Um, we have three presenters today. They are young, talented presenters, including my advisees. Let me present a ground rule. We have 13 minutes for presentation, and immediately 13 minutes there will be a first ring reminding 2 more minutes left. Then 15 minutes the second ring. That means the presenter has to finish, followed by 2 more minutes for question and answer in order to secure or maintain the quality of today's presentation flow. So without any further ado, let the first presenter present his research. Could you lend your hand to give the first presenter a warm welcome? Thank you.
Hello. Yes, and good morning, everyone. I'm James Leo Boreza, and from Michigan University of Science and Technology. And today I'm going to discuss to you about the evaluation of 3D printed acoustic materials for cooling fan noise reduction in a custom ISO aligned enclosure. So this is focusing on acoustic material performance for fan integration system. How? So to start with, cooling fans are widely known for thermal management because they're able to supply of volume of air, and also they're known for compact design. However, this cooling fan generates tonal noise, particularly in blade passing frequency. So there are many noise reduction. There are so many traditional acoustic materials that we have known. One of these is acoustic absorber that we see in the screen. So they can reduce noise, but they are dependent in their thickness, and this thickness results to restricting the airflow that comes from the fan. So the challenge: can we reduce fan noise without affecting airflow? So this study proposed a Helmholtz resonator-based acoustic metamaterial ring. That this resonator can reduce the specific noise, which is blade passing frequency, through their destructive interference, and also maintaining the compact design, and also without blocking or affecting the airflow that comes from the fan. So the research objective is to evaluate the effectiveness of this acoustic metamaterial, a compact Helmholtz resonator for cooling fan tonal noise reduction. So this study aims to identify the tonal noise that comes from the cooling fan, and also acoustic metamaterial. Fabricate, to create acoustic metamaterial using 3D printing, and also to evaluate the acoustic performance of this proposed material or design. So the selected cooling fan has 9 blades in it, and also 9,200 revolution, mean the rotation speed of the fan. And the theoretical BPF that we know is 1,380 Hz. That is the theoretical blade passing frequency of this fan. So this is the collective actual measurement of the fan. And the theoretical BPF, is here from the red line. And this is the actual BPF range of 360 Hz of BPF. To target a single frequency, so we consider having a target frequency design about a near frequency of 1,330 Hz. So we design about that can resonate about the 1,330 Hz of resonator. So this is the ideal pedal setup that has a noise generator, resonator sample inside, and also the microphone. So
James, can you use the last point? Yeah.
okay. Thank you. So this is the noise generator usually, then microphone, and also the resonator sample. But this setup uses a fixed frequency. So then in this study we consider of evaluating the effectiveness. So this is the study of using a simulation, studying inside the only. So this is the air property, not the whole impedance tube. So we consider the effect of a different cavity shape, starting with a sphere. So here is the sphere. This is the internal geometry of the resonator. So then this is a cylinder and also parallel pipe resonator. And also, we consider also the different combination of the neck parameters. So there is a small or large hole or diameter, and also the short or long neck. With the help of ANSYS, specifically in harmonic acoustic, so we are expecting to see the transmission loss. So how much the transmission loss that can resonator perform, and also we consider also the pressure distribution, frequency response, the destructive interference, and also the compactness of the design. So the result of the simulator is spherical resonator with a small hole, short neck, or in short, a smaller parameter design, provided a good balance between transmission loss and compactness. Here it shows that the sphere show the transmission loss happen at 1350, near to the targeted frequency. So then, because of the spherical resonator help reduce internal acoustic reflection, unlike to the other such as a cylinder, it introduced the increase of internal reflection inside, and resulting to increase of maximum pressure that creates, that resulting to have a transmission loss far away from the targeted frequency, which is 1330. Here it shows the effect of the different neck parameters. It shows this shows that the neck geometry strongly influence the resonance and also the transmission loss. Here, having a larger neck parameters, it shows that the cavity itself become larger structure that affects the compactness of the design. So it shows that this neck, this is optimized resonator design. The smaller design of the neck, and also shows that good balance between the acoustic performance and also the compactness of the design. Optimized resonator is arranged into a ring design of this to form a acoustic metamaterial ring. So these are equidistant to each other, having one ring is 8 resonator, 12 resonator, and 18 resonator. So I'll show you the 3D printed result. So in the experiment setup, since in this setup we don't have the impedance tube in the meantime. So, and having a actual experimental setup, this will make sure that we will have a real fun operating experiment that we can evaluate for the study. Using this ideal setup, there is a main source, the noise source, which is the fan, and also at least 1 meter away from the noise source. And data acquisition system, and this is about the microphone, the distance of the microphone from the noise source, and also the monitoring system, which is the computer. So here, ISO aligned acoustic enclosure. This is our build to make a controlled environment for this kind of study, to measure the real operating fan noise of that creates of this selected fan, with or without the AMM, so we can measure the noise reduction performance of. So, optimized AMM ring configuration shows that having 18 resonator AMM achieve the best performance and showed consistent, repeatable results. So here's the baseline of this paragraph. Shows that the 18 resonator AM ring reduced up to 2.1 decibel of noise reduction. So the effect of AMM resonator ring configuration shows that increasing of number of resonator also improve the noise reduction of the proposed design. And also, this resonator ring improve the circumferential coverage because of the arrange of the resonator within the metamaterial design. So, and also, this compact memory achieve almost 40% acoustic power loss. So even though this is compact, a single ring, it shows a compact acoustic power loss of almost about actually 38.5%. So almost 40% of the acoustic power loss it performed. So in conclusion, this passive acoustic metamaterial ring performed that a noise reduction at a specific frequency, which is the plate passing frequency. And also it shows that the resonator design, the optimized resonator with a smaller neck parameters with small hole and short neck showed the best performance and compact design. And also it is significant and also show a strong potential for electronic cooling noise reduction application. So that's all. Thank you for listening.
You come up with an ISO-aligned impedance testing instrumentation without low cost, knowing lots of previous researchers spend a lot of money to do this kind of research, but you use it almost like homemade.
Actually, I'm very thankful to our advisor for helping me with this, building a simple, customized ISO. Actually, to create a control environment. This is
Just 1 minute.
okay. So, this is the purpose of this customized acoustic enclosure is to isolate the fan noise from creating a additional reflection, to create a repeatable and reliable results. So this is not totally perfect ISO aligned, but the idea of ISO is to not create additional reflection that resulting to have a non-reliable results. So that's
All right. The reason I brought this question is not just for him, but for the upcoming two representatives, because I found a common denominator for this session, which is they use very different methods or intellectual excellency to overcome what seems to be a problem to face the very well-known problems. So let's keep looking for that. Now we are open for the question and answer. No more time. Okay, thank you. Then we welcome the second presenter.